So we did examples like this. When we first began, we said cross, for example, two heterozygous plants, if you remember. And heterozygous means not the same. So, is it on here? So heterozygous would be like big G, little g. That's heterozygous because they're not the same, correct? Can you see up there behind me? Okay. Two heterozygous means both are like that. That's how we began our lesson, right? And then we said, what kind of gametes can you get from this individual? And this individual can give you a big G or a little g. Only one can be given because the other parent will give the other one. And then the other parents can also give a big G or a little g. And then we decided we have to do a Punnett square. And it's going to be a 2 by 2 because there's 1, 2, 1, 2. So I need a Punnett square that's 2 by 2. Something like that. So I got 2 boxes up top, 2 boxes on the side. One parent goes on one axis, the other parent goes on the other axis. Jeremy, you have to leave, keep talking. So big G, little g, big G, little g, and then we filled in the boxes, side and top, and then again, side and top, again, and we'll always put the uppercase first, and then side and top, like that, right? And then we were going to show the genotypes. So one of the 4 boxes, so 1 out of 4 is big G, and then 2 out of the 4 were big G, little g, and then 1 out of the 4 was little g, like that. That's our genotype. And then the last step that we mentioned was figure out the phenotypes. And the phenotypes are, all of these have the big G. So 1/4 plus 2/4, that's 3/4 are going to be green. And then 1/4 was going to be yellow. So we're only looking at one gene. This is the gene for color, and the gene for color, only one gene, correct? And then we moved on to 2 genes. And with 2 genes, we went to what's known as a dihybrid cross as opposed to monohybrid. So with 2 genes, or dihybrid, di meaning 2, hybrid meaning they could be different, we had problems like this, which is where we left off. So it was the mice story, and we're given a key. We're told that mice can be normal or running mice, so they can run. Or mice can have a defective gene and they wobble, they can't run straight, and they like to call that the waltzing gene, which is a sweet way to say messed up muscles. And then we said the fur color, this is all from the package, mice can have black fur, or they can have brown fur. Okay, and then we're given a problem like this. I'll be right with you. We're given a problem like this. So we're told, okay, that tech deck is completely inconsiderate. I'm going to walk up there and if you have issues, stop doing that. Okay, so, hey, Henderson. Yep. Okay, one where it says cross a heterozygous running. So that means, that was number 1. Heterozygous running means like this, because that's heterozygous running. So cross a heterozygous running, heterozygous black. So this is where we learned that also the dominant is the one that shows. So even though it's heterozygous, it's going to be running in black. Because the waltzing and the brown are, sorry, this is B, are recessive, so you don't show it. So cross a heterozygous running, heterozygous black mouse with a homozygous running. So that's going to be like that. Homozygous running, homozygous black mouse. So we left off somewhere here. And then let's figure out, this part was a little bit tricky. You have to figure out what can each one contribute. And each parent must give 1 for each of the 2 genes. 1 out of here, 1 out of here. So you must have a running gene and a fur gene. So this parent could give, and we used the form method for that. So we said this parent could give the running with the black fur, or you give the running with the brown fur, or you give the wall waltzing with the black fur, or you give the waltzing with the brown fur. The other parent, much easier, can only give one thing, the running and the black fur. That's it. There's always running, always black, correct? With me so far? And then if you design the Punnett square next, the Punnett square is going to be 4 by 1. I can make it longwise, I can make it sideways. I will make it, I'll make it sideways just so we don't use too much of our paper. So we'll go like that, sideways. And I need 4 boxes for one of the parents. 1, 2, 4 boxes. And the other parent only gets 1. So that's going to be putting this parent on one axis. You may not put more than one parent on axis. Each parent gets his axis. The other axis, you get this parent's contributions. I'm just copying these from up top, and then that. That's the last one. And then I just do the same thing, sideways and top. So I'm going to go, okay, big R, big B, sideways and top. Big R, big B, little b, sideways and top. Big R, big B, and then big R, big B, little b. And nothing repeats, they're all different. So I can actually say 1/4 would be like that, 1/4 would be like that. There's 4 boxes, so out of the 4 boxes, 1 and 1/4 like that. And then, so that'll be my genotype. And then for my phenotypes, everybody that has an uppercase R and B is black. That's a running black, that's a running and black, that's a running and black, because it's dominant, that's running and black. So for my phenotypes, they're 100% running and black. So even though I have 4 genotypes, I only have 1 phenotype. And that was the second type of problem we did. 2 genes, so it's a dihybrid cross. Cool?